Hi, I'm happy to present my work, Cross-Attentional Audio-Visual Fusion for Dimensional Emotion Recognition. This work was done along with my professors, Eric Granger and Patrick Cordiner. This is the outline of my talk. I will briefly introduce the problem of dimensional emotion recognition. I will present the motivation of a proposed approach, the proposed approach, followed by results and discussion, and finally, conclusion. Introduction to dimensional emotion recognition. Dimensional emotion recognition is the problem of estimating emotions on a continuous scale as regression values in the valence arousal space. Valence represents the range of emotions from being extremely sad to extremely happy, and arousal reflects the energy or intensity of emotions being expressed from very passive to very active. AV fusion for dimensional emotion recognition. Audio and visual modalities are widely used contact-free modalities in the field of affective computing. They provide complementary relationship so that we can be able to obtain comprehensive information. Therefore, if we can efficiently fuse the audio and visual modalities by leveraging the complementary relationship, we are expected to have better performance than unimodal approaches. Challenges in audiovisual fusion. One of the major challenges is how to extract efficient multimodal feature representation in fusing audio and visual modalities, and how to efficiently leverage the complementary relationship of audiovisual modalities for better performance. And we can see wide range of variations in facial expressions like pose, illumination, identity bias, etc. Similarly, we can have wide range of variations in vocal expressions like speaker identity bias, background noise, etc. Motivation for cross-attentional audiovisual fusion. These are some of the approaches for audiovisual fusion for dimensional emotion recognition in the existing literature. One of the earlier works was done by Zirakis et al., where they have extracted audio and visual features from Resonate 50 and 1D CNN respectively, which is further concatenated and fed to LSTM for the prediction of valence and arousal. And recently, Shonival explored knowledge distillation for visual modality and 2D CNN for audio modality using spectrograms, which is further concatenated and fed to LSTM. Zirakis investigated various kinds of fusion strategies along with attention mechanisms, including self-attention. Parthasarathi and Sundaram explored transformer based approach for cross-modal attention where audio-visual features are integrated into the module of self-attention in transformers. Limitations of the existing literature. Most of the existing approaches have focused on modeling the intramodal relationships. The intermodal relationships across the audio-visual modalities are not effectively explored to capture the complementary relationship. Though attention models have been explored with transformers, they fail to explicitly capture the complementary relationship of audiovisual modalities. Finally, the semantic relevance among the audiovisual features are not effectively captured in the existing approaches. Inspired by the limitations of the existing literature, we have focused on modeling the intermodal relationships using cross-attentional fusion. In cross-attentional fusion, we estimate the cross-correlation across the audiovisual features to capture the complementary relationship. The cross-correlation across the audiovisual features helps to interact between the modalities and to measure semantic relevance across audiovisual modalities. Cross-correlation based cross-attention has been previously explored in classification tasks such as few-shot classification and weakly supervised action localization. But in this work, we have explored cross-attentional audiovisual fusion based on cross-correlation in the context of regression. Proposed approach. In the proposed approach, we have three major modules: visual network, audio network, and cross attentional fusion. This is the overview of the proposed approach, where we have a given sequence. We decouple the visual and audio streams and we feed the visual stream to the pre-processing block, where we can be able to obtain the facial regions and feed that into the visual feature extractor in order to obtain the visual features. Similarly, the audio stream is fed to the pre-processing block to obtain the spectrograms, which is further fed to the audio network to obtain the audio features, which is finally fed to the cross-attentional audiovisual fusion module to obtain the audiovisual feature representation, and which is finally fed to the fully connected layers for the prediction of valence and arousal. I3D is widely used for action recognition. Inspired by the performance of I3D, we have explored I3D for visual feature extraction. Specifically, we have used Inception V1 architecture as our base model, which is inflated from 2D pre-trained model on ImageNet. For audio modality, spectrograms are obtained from the speech signal and fed to the 2D CNN, which is trained from scratch. Cross-attentional audio-visual fusion. Finally, the audio and visual features are fed to the cross-attentional module in order to obtain the audio-visual feature representation. In cross-attentional audio-visual fusion, we first estimate cross-correlation matrix, where W is the learnable parameter, and then we estimate the cross-attention weights, where we can observe that the cross-attention weights of audio and visual features are estimated by applying softmax on the cross-correlation matrix Z and Z transpose respectively. And then we obtain the attention maps based on the cross-attention weights of audio and visual features. Finally, we add the attention maps to the original features, which is further fed to the TANH activation map in order to obtain the final attended features. Finally, the attended features are further concatenated and fed to the fully connected layers for valence arousal prediction. Results and discussions. We have evaluated the proposed approach on two datasets, Recola and fatigue dataset. Recola dataset has been used for various challenges like AWEC 2015 and AWEC 2016, where 9 subjects are used for training and 9 for validation. Fatigue is a private dataset which has 27 videos captured from 18 participants suffering from degenerative diseases inducing fatigue. For all the experiments, concordance correlation coefficient has been used as the evaluation metric to measure the performance of the proposed approach. Ablation study. We have done a series of experiments in order to validate the proposed approach, where we have used 2D CNN and 3D CNN for visual modality, and for audio modality, we have used the same deep network for all the experiments. For fusion, first we have used simple feature concatenation based approach, where we have concatenated the audio and visual features and fed to the fully connected layers for the prediction of valence and arousal. And then we have used LSTM based model, where we can see slight improvement over the previous approach. We have also evaluated self-attention based fusion strategy and compared it with our proposed approach. These are some of the visual results of some of the subjects in the development set of Recola dataset. So here we can see, though we do not have a clear frontal face, still we can be able to track the ground truth because we are leveraging the audio modality. Comparison with state of the art. So here we can see we have compared the performance of the proposed approach with several state of the art approaches. And we can clearly see that the proposed approach clearly outperforms the performance of the state of the art models. For fatigue dataset, we have used 80% of the data for training and 20% for validation. And here we can see the results with audio only, visual only, and simple feature concatenation and the proposed approach. Conclusion. We have proposed a cross-attentional audiovisual fusion model for dimensional emotion recognition. Unlike prior approaches of audiovisual fusion for emotion recognition, which has focused on modeling the intramodal relationships, we have focused on intermodal on intermodal relationships to leverage the complementary relationship of audiovisual modalities. Contrary to prior cross-attentional models we have explored in this approach, cross-attention based cross-correlation in the context of regression. An extensive set of experiments are conducted on recall on fatigue datasets with various baselines using fusion strategies. Thank you so much.